In the last video, we took a look at conserving momentum in one dimension. Here we'll go ahead and take a look at conservation of momentum situations in two dimensions. And I'll start with a situation that was actually fairly harrowing for me. I was microwaving some food on a clear glass plate. And when I pulled it out, I noticed that the plate got pretty hot, and I had set it down on the counter. And when I set it down on the counter, what I didn't realize was that I had set it onto a small puddle of water. This created one heck of a thermal shock. And I noticed the entire glass plate shrink a little bit. I noticed it oscillating in size. And my first thought was, wow, that's really cool. And my second thought was, duck! And sure enough, when I ducked, right after I ducked, the plate broke into pieces and flew all over the place over my head. I wound up picking out chunks of plate from the wall. Good times. So let's analyze a version of this. Let's say that the plate broke into three pieces of equal mass. Maybe like this. I'm not saying that's what actually happened with my particular plate, but just to make the numbers clean. And let's say that we know that this plate here flew off, this chunk of plate here flew off at 10 meters per second straight up. And this piece here flew off at 10 meters per second straight to the right. What I'd like to know is what is the magnitude and the direction of the velocity of my third plate here. So I'd like to know the magnitude and I would like to know the direction. So I'll need to work out the angle here. There. Well, the only forces that were acting on the plate that were external to the plate, so we're making our plate the system here, were the force of gravity pulling the plate straight into the screen and the normal force pushing the plate straight out of the screen. These two forces cancel, which means the net force on the plate is zero, so we can treat the plate as isolated. Since we can treat it as isolated, we can then demand that the total momentum after the explosion, a physicist would consider if you end up with more objects than you started with, that's an explosion. The momentum after the explosion has to equal the momentum before the explosion. Now here we've got pieces of plate flying off in all directions. So we will have to express this momentum conservation in both x and y. So when I go and look at the x component, I see, okay, this piece of plate here is flying straight to the right. So its momentum is directed entirely along x and its magnitude is mv2. This piece here is moving left and down. So we'll have to find the x component of it. So we can put in a minus sign because we're going left. And I've made its mass equal to m as well. And we can put in a v3. And now we just got to figure out whether we're doing a sine, a cosine, or a tangent here. So let's just draw this over here. v3. Since we want to find this angle theta here, it probably makes the most sense to use that angle for my reference. I can see that this is an adjacent leg, so that will make it a cosine of theta that I will need. All right, and what was the total momentum before? Well, before, the plate was at rest. If the velocity is 0, the momentum is 0. And that's true both in x and y. All right, now let's do this again in the y direction. So in the y direction, we first look for anything that's moving upward. So here, this is going up, so it'll be mv1. In here, this piece is going down, so this will be minus mv3. And that piece is an opposite, so that would be a sine theta equals 0. Now you'll notice here that I'm doing things a little differently than I do in one dimension. In one dimension, I would have used plus signs for all the momenta and handled the directions when we substituted in the numerical values. What I find is that in two dimensions, usually you've already got a pretty good idea of the directions, and it will make more sense for you to already assign the signs by hand. So I do implicit signs in one dimension, and I do explicit signs in two dimensions. All right. So let's go ahead and see what we can do with this. First off, we can divide everything through by m in both equations. So m, and of course 0 over m is just going to give me m. Same thing here, and dividing by m there. 0 over m again just gives me 0. All right, so we want to find v3 and we want to find the angle. In this case here, I think it's going to actually be easiest to find the angle first. And what we can do is just express this as v3 sine theta equals v1. And then what I'm going to do is this I can express as v3 cosine theta, and that would equal v2, but what I'm going to do is just divide the equations. So what that does is it cancels the v3's and leaves me with a tangent. So I have the tangent of theta is equal to v1 over v2, or theta will be the arctangent of v1 over v2. Here, both of those are 10 meters per second. And good thing here, the units cancel. Remember, whenever you are taking trig functions of things, the argument better not have any physical dimension, because otherwise it'll make no sense. So we got that the angle is 45 degrees. Super. Now that we got that the angle is 45 degrees, we can pick either of these to get my v3. So I'll use this one. So that one gave me v3 sine theta equals v1. So v3 will be equal to v1 over sine of theta. So that will be 10 meters per second over the sine of 45 degrees. And that will give me 14 meters per second. So that's how you treat an explosion. An explosion just means you end up with more pieces than you started. But again, you just add up the momenta of all the pieces before and all the pieces after and balance. And again, when working in two dimensions, unlike one dimension, in one dimension, it's usually easiest to put plus signs in front of all the momenta and handle the directions at number substitution time. In two dimensions, it's usually easier to explicitly keep track of all the signs yourself. So I'll conclude this video by doing one more example. So let's say you've got a sheet of ice. And here I will have a 1 kilogram object going at, let's say, V1 initial of 5 meters per second. And then I have another object that's free to slide on the sheet of ice. We'll say its mass is M2 is 2 kilograms. Now what's going to happen is the 1 kilogram, and this is initially at rest, so V2 initial equals 0. So now what's going to happen is I've got this sliding in, so that's going to strike a little bit off center. When it strikes off center, what's going to happen is the two pieces are going to go flying off in different directions. So this piece, let's say, flies off this way, and when we get here, this piece, my M1, let's say it flies off that way. What I'm going to ask for is what the magnitude of both of these are given their angle with the horizontal. So what I'm going to do is pick a coordinate system like this. This puts the initial velocity entirely in x. Since the other object's at rest, this will have the advantage of at least making the initial y component of momentum 0, which will make this problem easier to solve. So we need the angles we scattered off at. Let's say theta 1 final was measured to be 30 degrees, and theta 2 final was measured to be 40 degrees. So here I will make my system the two pucks or whatever that are sliding on the ice. Because it's ice, we'll just go ahead and make it frictionless so we don't have to worry about any force of friction. Again, there's gravity going into the screen, normal force going out of the screen, but they cancel. So since they cancel, the net force is 0. That makes the system isolated. Since the system is isolated, we are allowed to demand that the total momentum after the collision be equal to the total momentum before the collision. And again, we will need to do this in components. So let's go ahead and take the x component of this equation. So afterwards, you've got two pieces that are both moving off to the right. So object 1, its total momentum is m1 v1 final. Now if I look here, I need to get the x component right here. This bit right here is the adjacent leg. So by SOHCAHTOA, that's going to give us a cosine of theta 1 final. And since the other object is also moving to the right afterwards, we'll put in a plus sign. Same kind of logic here. The total momentum of object 2 would be m2 v2 final. But we just want the x component. And again, the x component is going to be this piece right here, which is going to, again, be the adjacent leg, giving me a cosine of theta 1 final. Now, initially, all we have is m1 v1 initial. We don't have to take any components because it's directed entirely along the x-axis. M2 was not moving initially, so it does not contribute to the total momentum. So in a situation like this, when you're striking a stationary object, almost always you want to rig it up so that your x-axis is aligned in the initial direction of motion. We'll see that this makes the y equation much more straightforward to handle. So let's write the y equation. Again, afterwards, the m1 is flying upward-ish, so that'll give me a positive y component momentum, m1 v1 final. And here I need this piece right here, which that's going to be an opposite, so that would be sine theta 1 final. And then The only other piece we have after the collision is this piece here. It's going in a generally downward direction, so we pick up a minus sign because of that. The total momentum would be m2v2 final, but again, we just want this piece of it right here. That's going to be the opposite. So again, we need the sine of theta 2 final. And sorry about that right there. All right, now what about the y component of the momentum initially? We already know m2 isn't moving, so that's 0. But here, because we set the x-axis to go along the direction of motion of the one thing that was moving, this has no up and down component at all. So that means the initial y component of momentum is 0. Okay. And although what is going to go ahead is a pretty tough slug of algebra, I'll make it very clear that for the moment we're done with the physics. We've set up our expression for momentum conservation. And we're just having to do some algebra. The algebra is going to get a little yucky. Not too much you can do about it, but fortunately by having chosen the x-axis to line up with v1 initial, it'll make it a little less awful. So we will start with the y equation of motion. The strategy I'm going to have is I'm going to formally solve the y equation of motion for v2 final, and I'm going to stick that solution into the x equation. So let's go to it. So m2 v2 final sine theta 2 final equals m1 v1 final sine theta 1 final. So my v2 final will be equal to, divide through by m2, gives me an m1 over m2, v1 final, divide through by sine theta 2 final, gives me sine theta 1 final over sine theta 2 final. And just as a quick aside here, you may feel tempted to insert numbers here. I beg you don't. It may look like it cleans things up, but it would actually complicate things even more than what this horrendous mess is already going to be. So anyway, let's go ahead and take my formal solution for v2 final and stick it in here. So now this will give me an equation in v1 final. And it's not going to be terribly pretty, but here we go. So we'll start by just writing the equation. So we've got, m1 v1 final cosine theta 1 final plus m2 from here. Now I need to put all of this in for v2 final. And then remember there's still a cosine theta 2 final waiting for me at the end. So v2 final is m1 over m2 v1 final sine theta 1 final sine theta 2 final. Now I still have this cosine theta 2 final here equals m1 v1 initial. And this is why I was begging you to not stick numbers in right away. These m2s cancel. With those m2s canceling, now look at this. All of these m1s drop out, cancel out from each term. That saves us a lot of grief right there. So now we can go ahead and collect some terms. So there's a v1 final in both of these. Since we're solving for it, we need to group it out. So we pull out a v1 final. This term gives me a cosine theta 1 final. All right, this is still a bit of a mess here, but we can clean it up very slightly. I'm going to write this sine theta 1 final here. But then here I'll have a cosine theta 2 final in the numerator and a sine theta 2 final in the denominator. And if we remember our trig identities a little bit, cosine over sine is cotangent. So just to make it slightly easier to write, I'm writing cotangent of theta 2 final there. And this equals V1 initial. So now all that's left to do is divide by everything in the parentheses, and we'll have our V1 final. So V1 final equals V1 initial over cosine of theta 1 final plus sine theta 1 final cotangent theta 2 final. All right, and now we can stick in the numbers. So this will give me 5 meters per second over the cosine of 30 plus the sine of 30 degrees times the cotangent of 40 degrees. Run that through your calculator. You get 3.42 meters per second. And you look at that and say, well, does that make some sense at least? And the answer is yeah. You know from your common sense it needs to be more than 0 and less than 5. So at least there's that. All right. Now that we've got our V1 final, we can go back to what we had formerly solved to get my V2 final. In fact, I am just going to copy and paste it. All right, so all we need to do now is just substitute in the values and see what we get. So we have 1 kilogram over 2 kilograms, 3.42 meters per second from before, sine of 30 over the sine of 40, and that works out to be 1.33 meters per second. And again, that makes some sense. It's more than 0, it's less than 5. So that seems pretty sensible there. Alrighty. So in the next video, we will go and take a look at the extension of linear momentum to angular momentum and take a quick look at conservation of angular momentum. Catch you in the next video.